I'm excited to get up here and present. This is a little bit lighter weight topic than AI scary things, but I'm going to talk about data lakes. And hopefully this is a good way to ease into the end of your day. I know it's been a long day. You're all sitting here. Your brain is full. I know mine is too. So let me go through this a little bit. So I'm going to talk about data lakes, but first let me tell you a little bit about myself. My name is Brian Davis. I'm principal software engineer at Red Canary. I'm part of the architecture team. So I build security tools for other people, and I like to build things. I like to geek out about how things are built. So that's what I'm going to talk about today, is how data lakes work, because oftentimes you hear about the architecture of data lakes, and it's like, how is that even possible? I've been doing this for a long time, and it's actually a lot more than 2 decades, but I'm afraid to update this chart now. But also, I'm a hiker, I'm a photographer, I'm a home automator, and I'm a beekeeper, and I'm based here in Denver, so this is an easy trip for me. So here's what I'm going to talk about today. I'm going to start by talking about a SIEM. SIEM, I don't know what you want to call it. I call it SIEM. How you use it and why it's so expensive, right? And then I'm going to kind of pivot into a data lake. What is a data lake, and how do you build one, and what are the security use cases? Now, I want to start by saying I'm not here to throw shade on SIEMs. They absolutely have a place in our security environment, and that's the point that I hope you come away from here. But I want to talk about how a data lake can augment that, but more, I kind of want to demystify what a data lake is. Because there's a lot of talk about how awesome they might be, and you're kind of looking at that going, well, that kind of just doesn't sound right. That doesn't make sense. It doesn't pass the sniff test. One other thing I want to share is that every single image in this chart deck is either stolen shamelessly from the internet or hand created by me. So there's no AI in this chart deck at all. So hopefully I don't know if you'll appreciate that or not. But okay, so here's your SIEM. It looks exactly like that in your environment, right? It's that little box on the right-hand side. So then you want to go start storing stuff in your SIEM, right? And it always starts with, hey, let's go put database logs in the SIEM, because that's what the cool kids are doing. Then you start putting your web proxy logs in. Maybe you don't have a web proxy. Then you put firewall logs in. Then you start putting your Active Directory logs in, because those are pretty important. Then you start putting your NetFlow logs in. Then you start putting your OS logs in. Then you start putting your web app logs in. Then you start having your server logs come in, because someone comes in, oh, you know, we need those server logs because I didn't have context during that last incident that we had. Then you start putting your VPN logs in there, because that's also pretty important. Then you maybe want to put your physical security logs in there, because maybe someone's in the building, maybe you don't have a building, maybe you don't have that. Then you have identity provider logs. So you see, you just kind of keep adding more and more. And then someone says, hey, let's put your EDR telemetry in there too. Endpoint detection and response, which is huge. And you start funneling that into your SIEM, because it's really, really useful stuff, but it's really big. Or, hey, let's go put our cloud logs in there. So ultimately, your SIEM now looks like some sort of bizarre jellyfish. And meanwhile, your SIEM budget is bursting at the seams, because you're pushing all of this data into that, which probably makes your finance people pretty upset. So why is this the case? Why is it that a SIEM costs more money when you put data in, right? And again, I'm not throwing shade on SIEM vendors. This is how the technology works. So let's talk about what a SIEM is under the covers. And again, this is a super oversimplified example. And because I don't work for a SIEM company, I can't tell you about how a SIEM really works. So I'm going to use OpenSearch as a proxy, because it's open source and we can talk about it. And it's kind of SIEM-like in a lot of respects. So let's say you have an OpenSearch cluster, and you have some sort of control plane node. And then you have another control plane node, because redundancy is all cool, and you have all these things. Then you have these monster-sized data nodes that are sitting out there. These are really big computers, and they have really big disks. You can see how big that disk is. That's actual life size, or at least it was a long time ago. But you have a lot of these. So you have these big computers that are running somewhere. Maybe they're on-prem, they're probably in the cloud, and you're paying a lot of money to run all these computers. So that compute is really, really expensive. And that storage, it's relatively cheap. And I'm going to show you some numbers related to that. And there's one simple truth in cloud computing or IT, and it's that renting computers is really expensive, right? We've all learned this lesson. You've all spun up an EC2 instance or your favorite cloud provider of choice. And you say, oh, that cost me a lot more money than I thought it was going to. So let me give you some examples. So these are numbers that I pulled from a cluster that we run that has 105 terabytes of storage on it, which I don't know if that's big or small, it depends on your organization. But this is a good example for what OpenSearch would cost me to run in AWS. So these are all just AWS numbers. So that OpenSearch cluster would cost about $25,000 a month to run. All right, maybe that's a big number, maybe that's a small number. Again, depends on the organization. As a human looking at that number, I say, well, that's really a big number. But companies can spend a lot more money on this. Now you can look that about $8,000 of that is on the storage, and then the rest math in public is the compute. What if you could just put that data in S3 or Azure Blob Storage or some cloud blob storage that exists out there? It would only cost you $2,500. That's a lot cheaper. So maybe if we can get this stuff onto just storage, maybe magic could happen. And then if you put it into cold storage, like Glacier Deep Archive, it's like $100 a month, which is kind of absurdly cheap. Now you can't get to it very quickly, but maybe that's not a use case that you have. So now you're starting to look at, well, here's a cost profile for running OpenSearch yourself to do this kind of SIEM-like function. So let's go back to this cluster that I told you about, which is 432 cores of CPU and 3 terabytes of RAM. That's the cluster. Again, I'm pulling these from an example that we have in-house. So that's a lot of compute. That's a lot of compute. And why do you have all that compute? Obviously, it's ingesting all of those tentacles of a jellyfish. I don't know what, I'm an engineer. I don't know what jellyfish have, but it's taking all that data in, and that's obviously work that it's doing, but I don't know that that's 432 cores worth of work. A lot of those cores are so that you can query the data, and a lot of those cores are just there because you need that much infrastructure to have that much memory because compute just gets kind of bigger over time. So at this point, I'm now like 5-6 minutes into the presentation, and I haven't talked about data lakes yet, and you're probably going, I don't know about SIEMs, I don't want to hear about this. So the reason I'm explaining all this is because it really helps, I think, to pivot into data lake land, to understand how the magic has happened. So stay with me, it's gonna get exciting, and then there's mini golf later. All right, so let's talk about a data lake. So let's look at the definitions that you can find from the hyperscalers. Ooh, a data lake is a centralized repository that allows you to store all your structured and unstructured data at any scale. Cool. That sounds like marketecture to me and a lot of fancy words that doesn't mean anything. Microsoft's definition is about the exact same thing. Centralized repository, ingest, store, large volumes, yada, yada, yada. Google, centralized repository that processes and secures large amounts of data. Oh, here's the best part. But it helps businesses cut costs, manage data, and use AI. They had to get AI in there because that's really the important thing that all the cool kids are caring about. So, but let's really talk about what a data lake is, in the fact that it's just gluing the existing technologies that have actually been around for a very long time together, right? And so when you hear this term data lake come up all of a sudden, it seems like it's something new and magical that's come about, like large language models, which those are admittedly pretty cool and magical. But really, this is just a repackaging of technologies that have been around for probably 10 or 15 years. Or it's like 3 raccoons in a trench coat that are just pretending to be something else. I just included that because I thought it was fun. So let's go back to that OpenSearch cluster, because I bet you're wondering, why did he go through all that? He didn't talk about it. So if you look at this OpenSearch cluster that has an absurd amount of cores, an absurd amount of RAM, it costs a lot of money, and you say, boy, that compute was really expensive. Can't we get rid of that compute somehow? Because that would save me a lot of money. And let's just pretend this hypothetical game. I'm glossing over so many details here. We can absolutely talk later about that. But I really wanted to just get to the storage, because that's all I care about. I just want to store this data. I don't really want to pay for the computer associated with it. If I can get rid of those computers, now I'm down to $8,000 a month. Cool, way cheaper. So how can I do that? Well, I'm just going to make the computers go away. Bear with me. I'll kind of explain how this works a little bit. So let's pretend the computers go away and I just have these disks that are sitting out there in the ether in the cloud. Well, now my costs can be a lot more manageable. And now if I have these disks that are holding data, it doesn't need to be expensive block storage, which is the type of computer, the type of disk that you have to have attached to a computer. It could be object storage, because now it's disembodied. I don't know how this works. We can go through those details later. So now you can move that $8,000 to $2,000 worth of S3 storage. Suddenly it's getting cheaper. Wow, we're saving all this money just by deleting those boxes that you badly drew on the screen. So let's take a look at what the computer use pie chart would be. And this is totally hypothetical. I made this up. There's no data behind this. But if you think about it, those computers are idle most of the time, arguably. Right? And then there's some slice of it that they're ingesting the data. There's some slice of it that's querying, and the rest of them are just sitting there consuming power. So how do you solve this problem of computers that you're not using all the time? Well, the answer obviously is serverless, the other buzzword in cloud computing that's been around forever. Well, let's do some serverless magic on top of that. Stay with me. This will almost make sense by the time I'm done. So if I instead can do serverless computing on top of those disks that I have there and spin up computers when I need to go and query the data or ingest the data and then shut them down when I'm not using them. Ooh, I get the magic of the cloud. I get a lot of that cost savings because I don't have to pay for that compute sitting there idle all the time. There has to be some architectural changes under the covers to make this happen, and I'll talk through that. But this is starting to be where the magic of a data lake comes from. But then the cool thing is, when I have a lot of people querying data or I have a lot of data coming in, I can add more computers because they're all serverless. I can spin them up, right? And there's a lot of this magic happening behind the scenes when you're starting to look at this data lake technology that exists in the cloud. All right, so we add compute. Cool. That's all I need. That's all I need to do is to lower my SIEM bill. No, not really, right? Because I told you there are some architectural changes, because the thing is, the data that's been stored on disk for a SIEM is structured in a certain way to assume that there's a computer attached to it all the time. And that doesn't necessarily transfer to a serverless concept. So now we go back to those other concepts that have been around for a long time that we can leverage to take care of that storage. So I'm going to go way back now and keep this very simple, very horsey ducky, because it's late in the afternoon, but I like, simple drawings of what spreadsheets look like. So if you think about the data going into your SIEM, it's probably log data. And you could say, well, it doesn't look like this at all. That's a table. Well, at the end of the day, it's getting flattened down into a bunch of rows and columns. And you could just kind of bear with me. Or maybe it's a couple of columns of timestamp, what host name it came from, and then maybe a big JSON block. But you have these rows and columns of data going. So we usually think about data in terms of like a CSV, or horizontally slicing the data. And it looks like that when you write it out. We've all looked at CSV files. They're all super exciting. They're all fun to look at. And that's logical to look at from an understanding of, oh, as a human, I can see that and I can understand what it means. But it turns out this is a pretty lousy way to store data. Because what we figured out over years and years, not me, some very smart people, not me, is that if you store data in columnar format, you can gain a lot of efficiencies out of it. So if you look at it, what it would look like encoded, it says A1, A2, A3, A4. That's what I mean by columnar. So what this means is that I'm actually capturing the entire column of all my data and writing it on disk and encoding it that way. This isn't a new concept. This has been in data warehouses forever. But what we can do is kind of transfer this and use this technology combined with some of the others I've talked about to start storing data more efficiently. So when you look at it like this, you're like, I don't get it. Why are you showing me this? It's late in the afternoon. I don't really care about spreadsheets. Let's look at some real data, because I think it becomes more powerful and more obvious. This is a table of Kubernetes deployments that I dumped out because it was a good example that I could use. And it's a bunch of time-stamped snapshots of pods that are running with some IDs on, right? So there's the desired count, there's the run count, there's the requests, limits, and bytes, a bunch of repeated data. Cool. If you slice this as a CSV, it looks like that. Ooh, shocker. I know this is revelatory for late afternoon on a Thursday afternoon. So that's exactly what you'd expect it to see. If you dump out a table out of a spreadsheet, it looks like that. Everyone knows that. And I start writing down, I only did 3 rows because it gets kind of out of hand. And if I write those columns down in a file format known as Parquet, well, then it looks like this. And on the surface, that looks more confusing because as a human, I look at that and say, well, I don't really know how to read that. Well, that's okay. You're not a human reading this. Computers are reading it, and computers are really good at this. But you start to notice that I see the same data over and over again. That date, April 1st, then April 1st, then April 1st. Then I have a couple IDs that are sequential. Then I have the number 1 6 times. Then I have 1,000, 1,000, 1,000. I don't need to read through all this. It's not all that exciting. But what this gets you is natural compression in the data that you've written out. And if you think about a lot of the data that we write down, a lot of it is extremely repetitive. Not when you do it as a CSV, but if you start writing the same data over and over again and you can group it by columns, you can naturally compress this stuff out. Because now you look, you can see exactly how I described it. It's April 1st 3 times. It's some sequential IDs. It's the number 1 6 times. It's the number 1,000 3 times. It's the number 2. You get the idea. So this Parquet format, this columnar format, already lends itself to really, really good compression. And it actually turns out that from a searchability standpoint, this is why data warehouses use this technology, searching through all of the data in a single column is frequently what you want to do when you're digging through data that's really, really old. And if it's all in one place on disk, that's actually faster. So it's faster to query. It's much more compressible. So as an example, that CSV file, this is 5 million rows. put all 5 million up here, was 290 meg. Okay, cool, it's a big CSV file. When I gzipped it, it was 24 meg. The Parquet file was 8 meg, right? So already you're starting to gain significant compression just out of writing the file in a different format, just out of writing the data in a different format. And I included a picture of Parquet because if you're a certain age, you recognize that, and now that voice is stuck in your head, and you're welcome. And that's all I'm gonna say. So let's say you're writing all these Parquet files out because you decide that you wanna store your data in Parquet format because you saw me talk about this. It's like Parquet is the cool thing, it's what all the cool kids are doing. Well, now, if you wanna write these Parquet files out into S3 storage somewhere, that's great, but now you just have these disembodied files out there that you don't know how to go find stuff. Well, this is where some of the magic of a data lake comes in. So you have the data that you're writing out, but now you got to keep track of the data that you're writing out. And so you create these manifest files sitting on top. And that's going to list, hey, here's where all this data that you wrote on April 1st lives. Here's where April 2nd lives. Here's where April 3rd lives. So you have this manifest file. Well, you can start to see, well, now I have multiple manifest files. So I have to have this manifest list to keep track of all my manifest files. Cool. There's just more metadata. You can see this room on the chart. I can go up. Guess what's coming next? More metadata, a metadata file to keep track of your metadata list or manifest list that goes to manifest file. This is all insane. When you combine all this together, what do you get? Boring Voltron. No, you don't get boring Voltron. You get something called an iceberg table. Ooh, wait, he said table. Now we're starting to get back into data lake land. If you have talked about data lakes at all, if you have read about data lakes at all, you hear people talk about iceberg tables, or maybe they talk about Delta Lake tables or Apache Hudi. There's a whole bunch of different flavors that are out there, but Apache Iceberg is an open source standard that defines this file structure that basically allows you to do a whole bunch of magic that looks awfully databasey. Ooh, I went too far. Right? You look at schema evolution, partitioning, time travel, like snapshotting and then going back in time, and ACID compliance. Well, those are words that database people use. I'm not a database person, I hate databases, but you can start to pretend that those files that you wrote in a columnar format are a database or a database table, which is really, really powerful because now you can do a lot of really cool things with them. And then you don't have to worry about this file structure because Apache Iceberg does that for you, and there's a whole bunch of libraries that will help you deal with all that. So cool, I've got a table out there that acts kind of like a table, and I've glossed over a lot of details there, but let's say that's sitting all out in an S3 bucket somewhere, or in an Azure Blob Store, or in GCP. I'm on AWS the most, so those are the native languages that I use. So now I have this iceberg table. It's pretending to be an iceberg table. It's really raccoons in a trench coat pretending to be an iceberg table. I might have 3 other iceberg tables, maybe in another S3 bucket. Maybe I don't. Well, now I need a way to go and query those tables because I got to keep track of it, right? It's all about metadata. So I have to have this table catalog that's keeping track of this table lives in this bucket in this location. This table lives in this bucket. And so there's a whole bunch of tools out there that let you do this. And this is kind of the magic of the data lake concept, is that these are all existing technologies that have been around for a long time that now all the hyperscalers are slapping the data lake label on, and other vendors are also advertising from a data lake standpoint of saying, look, you can store your data in a rational way, and we can give you the tools to glue those together. And I'll kind of step through this a little bit more in the future, but if you've seen AWS Glue Data Catalog or Azure Data Catalog or Apache Hive, that's a table catalog. Likewise, now that you've got this data sitting out on S3, you need a way to query it, right? Because it's no good sitting out there on these fancy Parquet files and all this boring Voltron stuff. So you have to have a query engine. Well, that's AWS Athena or Azure Synapse or Google BigQuery. These are names that you've probably heard before. It's all in context with, I'm going to go search S3 for some data in a well-known format. And behind the scenes, when you go to AWS Athena and you type in a query for something that's sitting in S3, it's just spinning up computers behind the scene for you. That's one of the reasons why Athena can become really, really expensive really quickly if you're scanning a whole bunch of data. I'll talk about that in a minute. But again, these aren't new technologies. Behind the scenes, all of this is running on probably Apache Spark or even Hadoop, right? Not new technology to the scene. So you go and you query, you want to query some data, it goes and hits the table catalog. Then the query engine goes and queries those iceberg tables that are sitting out there and returns that data to you. So again, we're taking these older technologies, we're gluing them together in kind of a novel way, and suddenly it pretends to be a database. I was thinking earlier today that this is a lot of the way that like Docker works, right? Docker containers weren't a new thing when they came out. It was all a bunch of existing technologies, but Docker wrapped it all up in a single command that you could run that a human could actually wrap their head around, as opposed to a bunch of Unix and Linux geeks that really get down into C groups. So you might look at that picture that I had and say, well, this is nuts. I don't understand this. I don't want to understand this. Cool. If you ever looked at Postgres or MySQL, it's just as lunacy inside of it. Right? We don't look inside of these databases because we don't really want to know. That's really what's going on inside of a data lake as well. It's the same type of mechanics that databases have, but this is just hidden to us, right? We just log into a Postgres database and do our thing and not really care about what's going on in the background. Okay, so where does that leave us? So the bottom line is, because you're writing data to S3, you can store a lot of it, and you can store it really cost effectively. You saw those plots before, and the fact that 105 terabytes cost about $2,000 to store in live S3. Because they're just objects. And you can query a lot of data, which might seem kind of counterintuitive because they're sitting out on S3. But the thing is, you can spin up, or really things like Athena will spin up as many computers in the background to parallelize that query across all those S3 buckets, which is really other servers, for you. And so all of that mechanics is hidden from you as a user. And the thing is, this can scale because you're not limited to a single database server, or in my case, 12 shards of an OpenSearch cluster that are really, really hard to grow and shrink because there's disks attached to them. There's all this scaling that is going on, but it's hidden from you. It's obfuscated from you. When you're writing stuff to S3, there's scaling that S3 is doing behind the scenes. We don't see it, we don't know, we don't care, it just works. Same thing with AWS Athena. So the point I'm trying to get across here is that these data lakes allow you to do things that those traditional SIEM architectures don't. And again, it's not going to replace the SIEM architecture, but it really serves a good augmentation. So when I say it can scale, this isn't from personal experience, but I was sitting in Trino Fest this last year, and Netflix, of course, comes up and talks about how cool they are, and everyone admires Netflix. But they're talking about in their data lake, they have an exabyte of data, which I don't even have a mental model of how much data that is. With 3 million iceberg tables, and their largest iceberg table is 36 petabytes, and they ingest 10 petabytes per day. These numbers hurt my head. They delete 9 petabytes per day, and they do 600 commits per second, 500,000 queries per day. So the bottom line is, it can scale. Now, we're not all Netflix. We can't all pull this off. I very much recognize that. But the thing is, the technology is robust enough. And I know that I use S3 and I use Athena enough to know, yeah, those technologies do scale really well. Oh, and 2,500 unique users. So the bottom line is, again, because these are built on mature technologies, these are pretty battle hardened. This isn't a new concept. We just glued them together in a new way. So what's the catch? Well, you're not paying for that server up front. You're not paying that $25,000 per month. But if you query a lot of data, you get, right? Because those computers will still come back whenever you want to query that data. It's a good example. Just a couple of weeks ago, we had an engineer that was running a test on our internal data lake and managed to spend $2,500 over the weekend without realizing, because he was just querying a bunch of data. And it worked, and it was very trivial. And then you see the AWS bill like, oh, cool. That was some interesting tuition that we just paid to learn how not to use this. So that's an interesting catch. And this is why it may not replace your SIEM. It's a different use case. You pay on query as opposed to pay on just it being there. So that's a very, very interesting thing to realize from a data lake standpoint. All right. So do you want to build a data lake? And if you have kids, this song is also stuck in your head. You're welcome. So there's a couple key phases in a data lake. I'm going to kind of walk through some of the building blocks. I'm going to super quickly gloss over this because I can't tell you in 6 minutes how to build a data lake. But I'm going to list some of the tools out there so that you have an understanding of what the magic is behind the scenes. So first, you have that ingest phase. Now, if you go and you say, how do I ingest data into a data lake? I know for me, I come across a whole bunch of data science blogs, and they talk about all the data science use cases, which is really hard because we care about security, not data science, but you care about both. Most of the blogs, most of the literature is written around data science because they're the biggest users of this, right? It's only more recently becoming a security thing. So it's a little hard to find information about this that isn't focused on data science-y tools. But if you go out there and try to figure out how do I get data in there, there's a lot of out-of-the-box tools that most of the hyperscalers provide, including some other ones, right? So Amazon Data Firehose, Data Factory, pipelines in Azure, GCP Dataflow, all of these are just designed to output Iceberg tables into their particular cloud storage for a pretty nominal fee because they're all connected together. Or you can go with the old school one of Spark and Flink and kind of roll your own solution because it's all built in with Iceberg support. So then I talked about storing this data, and this is actually the most cut and dry. It's blob storage. It's S3. Now all the hyperscalers have special data lake formatted blob stores that are supposedly optimized to work better for these Iceberg tables. I don't know if they're better or not, but everyone recognizes this is where the puck is going, and so they're building tools that make this easier to do. If you want to process this data, right, with that both in terms of querying it, or maybe that's in terms of doing transforms on it or analyzing that data, there's a lot of tools. I mean, this list is somewhat ridiculous, and I totally cut this list off. It could have been probably 3 pages on a particular chart. But you've seen these names before, right? You know about Amazon Elastic MapReduce. You know Athena. Synapse Analytics, maybe you've heard of. Azure Databricks or Databricks. Google Cloud Dataflow. Apache Spark and Flink. You'll see Spark and Flink show up everywhere here because it's really kind of the backbone of all these technologies. And then lastly, if you want to explore and visualize this data, because you really want to be able to see it, there's a whole bunch of tools that are out there that let you just connect it directly to a data lake and query it. You know, again, the hyperscalers provide some. Apache Superset is a good open source example that's out there because you can connect that right on top. And I actually have an example of that. So cool, you're talking about all this stuff in S3 and all this data that you're storing out there, but I can't use that like a SIEM. It doesn't look like a SIEM to me. Well, when I pull up these graphs, it's like, that looks kind of SIEM-like. Maybe I could build a graph like that. These are from Apache Superset backed by our own internal data lake. And you can say, well, but that's coming from S3, that's Athena, that could take forever to load. Each of these dashboards took about 5 seconds. And I think we were querying a very large time range of data. And that's something that we couldn't do in our normal data stores. And suddenly it's like, oh, well, this does offer some interesting opportunities. And this is the query that we wrote to pull some of that data. There's lots of widgets on there. That looks like SQL, right? Maybe that's a language that you already know or something similar enough that you're using in your SIMs, or that you could have your detection engineer or analyst write, saying, I want you to go dumpster diving in my data lake and look for stuff. Go write a SQL query. Well, again, because all these technologies are masquerading as a database, you can treat them like a database, and it works shockingly well. Now, you could still end up racking up a $1,000 bill if your query doesn't quite factor in the right thing, and you'll have to learn that the hard way or not, but the technology is available under the covers. So what am I really trying to say? If you have too much data, right, this goes back to the beginning, and you can't put it in your SIEM, it's because it just costs prohibitive. A data lake's a really good place to put it because you can just dump it in there and maybe you'll go and analyze it or maybe you won't. Or if you want to retain that data for a longer period of time, this is another problem that we frequently face. You might be putting all that data in your SIEM, but you can only store 30 days or 90 days of it. And you want to go back and look at a trend over a year or 2 years. Dump it in a data lake because it can sit there idle on disk doing next to nothing. And you can even store it over in something like Glacier and it can be really, really cheap. And then when you need to go look for it, you can pull it back. And that also goes to the other use case of the write once, read never data, where you have to store it. You need to from a compliance standpoint, but you don't really ever intend to go back and look at it. That's where you really save money because you can put it in cold storage and it's just going to sit there costing you very, very little money, but you've got it and you can prove it to an auditor whenever you need to. And the last one, because it wouldn't be a good talk without talking about AI and ML, is the fact that data lakes and AI and ML are like best friends, right? Because when you have that much data available, you can train a lot of machine learning models based on it. You can do a lot of AI related work with respect to it. And so since you have it just sitting there accessible to you, you can use it for other use cases. So the bottom line that I really wanted to drive home here is that data lakes are a really cost-effective tool to supplement what you already got in your security toolbox. It's not going to replace your SIEM anytime soon. The use cases aren't quite the same and the cost profile is different. But sometimes when you want to hold on to more data or do more analysis or do more comprehensive things, a data lake is a great place to throw all that information. So on that note, I'll open it up for any questions if anyone has any.